Many problems that we encounter are time-related problems. These types of problems are known as work problems and involve calculating how long it takes for one or more agents, such as people or machines, to complete a job or task. The focus of such problems is on the rate of work. The rate of work is the fraction of the task that is completed in 1 unit of time. Thus, rate is expressed as a proportion and is the inverse of time needed to complete the task. Let's consider this work problem scenario. A public swimming pool can be filled with water using a wide hose and a narrow hose. 6 of the wide hoses can fill the swimming pool with water in 12 hours. 3 wide hoses and 9 narrow hoses running at the same time can fill the swimming pool in 8 hours. Determine how long it would take 5 narrow hoses to fill the swimming pool. We identify this problem as a work problem because it contains 3 components specifically associated with work problems. There is time involved, there is a task that needs to be completed, and the amount of effort to accomplish the task, which of course is the rate of work. Let's take a look at a simple example. If it takes Henry 4 hours to paint a wall, then Henry's rate of work, which is the fraction of the wall that is painted in 1 hour, is expressed as the proportion 1/4. Now suppose it takes Henry's friend, Isabella, 6 hours to paint the same wall. Then Isabella's rate of work can be expressed as the proportion 1/6. To determine the rate of work of the friends painting the wall together, we simply add their individual rates of work. So a simple but important equation for determining the length of time to complete a task is the rate of work, and for this example is 5/12, multiplied to the time needed to complete the task, which is what we are trying to determine, and that equals to the part of the task that was completed, and for this problem, the entire wall. Simply solving for t, and it would take Henry and Isabella working together 2.4 hours to paint the entire wall. Let's return to our original problem. As we carefully reread this scenario, the component that stands out is the different combination of agents used to complete the task. We have one combination of hoses to fill the swimming pool, a different combination of hoses to fill the pool, and yet a third combination of hoses to fill the pool. Now for any work problem, it's important that we know the rate of work for individual agents. In this problem, it's the hoses that are used. So let's find the rate of work for an individual wide hose. We still use the rate of work equation, but rather than solving for time, we solve for the rate of work. Using the first combination of hoses, we can simply transfer this statement into our equation. 6 of the wide hoses is the rate of work, and they fill the entire pool in 12 hours of work. Simply solving for this equation, the rate of work for an individual wide hose to fill the swimming pool is 1/72. To interpret this, it would take 72 hours for a single wide hose to fill the swimming pool with water. Let's consider the second combination of hoses. The rate of work is 3 wide hoses and 9 narrow hoses. They fill the entire pool and in 8 hours work. Since we already determined the rate of work for a wide hose, we substitute this value into the equation. We then simplify the equation and solve for the rate of work for an individual narrow hose. To interpret this result, it would take 108 hours for a single narrow hose to fill the swimming pool with water. Now that we know the rate of work for an individual narrow hose, simply multiplying this amount by 5 gives the rate of work for 5 narrow hoses. Utilizing the equation, we can now determine the time it takes for 5 narrow hoses to fill the entire swimming pool. It will take 21.6 hours to fill the swimming pool with water.